Welcome to Balcony E. This is talk about, I don't know why this keeps going forward by itself. I'm going to have to manage that. This is the data dichotomy talk. This is rethinking data and services with streams from Confluent. So Confluent's the company behind Apache Kafka. Is anybody unfamiliar with Kafka? Okay, all right, cool. Confluent was started a couple years ago by the core team that built the software while at LinkedIn. Jay, Neha, and June received some seed funding from LinkedIn, which is pretty neat, to start Confluent. We currently employ about 70% of the active committers to the Apache Kafka project. And we've been around for about 2 years, 2.5 years. Been here about a year. It's easily one of the best companies I've ever worked for. It's fantastic. So this is a talk about scaling. Scaling in terms that you're really maybe not thinking about, whereas petabytes or messages per second are common. This is all about how do you scale your organization? How do you scale with people, right? How do you scale teams, and how do you scale those things when complexity is added and scale comes in, right? So this talk is a bit around microservices and how microservices work and what they are. Microservices is a very common term. It's kind of polarizing. There are people that love it. There are people that hate it. But really, so it's a very useful pattern that love it or hate it, you can probably see an application somewhere. So what is it? So the biggest, easiest way to put it is microservices help you split this monolith, right? So you have a single process or a single code base or a single team. If you split it into microservices, you can split it up amongst multiple processes. You can break your app into different code bases and have different teams deploy at different times. But really the key to microservices is autonomy, right? The essence of what microservices is about are the ability to autonomously deploy them. So each service exists in this bounded context that, if taken down, changed, and brought back, shouldn't affect any other service. And really, the key to this really becomes most apparent when you're doing your deployment cycle, right? So teams should be able to take a microservice down, change it, without worrying about other microservices. Everything should be independently deployable. This allows you to scale with many teams, many users, many code bases. This pattern can be applied across the board. So autonomousness is where these services get their value, the independence of them, right? They allow scaling, but not just in terms of your data and your throughput, but the teams and the people that are building and designing and growing these systems. What happens when we grow with our monolith? What happens when the data increases, right? If we have these small services, you can potentially grow a lot easier. It reduces the complexity of growth, right? Because inevitably, companies are a collection of their applications, right? And all those applications must work together to some degree. And I've worked at a bunch of different organizations, including very large banks. And the way that banks traditionally build systems is very isolationist, right? So I have my data, I know what it looks like, and you have your data, and if we need to share it, we'll work it out then. And really, the way data moves between these systems is treated like an afterthought, right? So this afterthought is actually kind of important, and you need to start thinking about how data moves between these systems. And when you start thinking about how your data moves between these systems, you're forced in a service to think about this external world and this internal world. The external world is where I live and you live. All of our applications live in the external world. They've got to interact with each other. But inside my service, I'm the king, right? I get full control. So we should be designing for the external world, right? Designing the internal. But this independence comes with a cost, and it's unavoidable. By having this independence, there are trade-offs, essentially. So as an example here. So good object-oriented design tells us we can build this interface that's clean, it's got low surface area, We hide the state, we encapsulate it, so the state of the object is hidden in there, and you just have a couple of interfaces that you can get state from. And this allows for a lot of loose coupling, right? So you're encapsulating your objects, you can have loose coupling, you can change how it works on the inside without changing how it works on the outside. And in a monolith, this is fine. So if we have a single code base and we have a change that goes across a couple of these objects or hundreds of these objects, we can coordinate it in our monolith. I can make a bunch of changes and then redeploy the whole thing, and it works fine after testing. But really, the problem comes when you have changes that are going across multiple services that are independent, right? So maybe this team is run by a different team, and it's likely that the statements team is handling different code base than the services team. How do you deploy without interrupting each other's workflow? And this actually, synchronization is not a data synchronization at this point. This becomes a bureaucratic synchronization, right? You gotta make sure everybody's on the same page, things like that. So services, micro or otherwise, work best when requirements are isolated in a single bounded context. You don't have a ton of dependencies. And as a good example of a small, single bounded context, let's talk about single sign-on real quick. Single sign-on has really one function. It says authorize. Am I authorized? No. Yes, no, yes, no. The business service really, it would be unlikely that it needs to access anything inside the authorization, right? And that's the real value in a single sign-on service. Like when you have your Gmail account, you've authorized it. Twitter asks Gmail if you are who you are. Gmail says yes. That's it, right? So you can extend that with a bunch of services. The power is really, really apparent there. So single sign-on has a very tightly bounded context. But in the business world or in complicated organizations or the government world, you know, your core business services have a core set of facts. And they interrelate in a different way depending on which team is looking at them. So the orders and the inventory team could be running different queries to that data than the customers and inventory teams, right? So the futures of these complicated services are very tightly intertwined. And how do you resolve that, requiring encapsulation to be loosely coupled, but have the freedom to slice and dice the data as you like, right? So the problem with data systems is they have very little to do with encapsulation. Data systems and databases, in fact, are data amplifiers, right? You can take data in a database and query it in different ways, make it big, make it small, change the shape. So you have this services that keep data on the inside and hide it on the outside. And you have these data systems that amplify data from the inside to the outside. And really what this is the data dichotomy, right? So data systems are about exposing data, services are about hiding it. And these two forces are constantly pulling at each other when you're designing your systems. So they have different goals, right? So encapsulation is to protect against future changes, and databases and data systems provide this flexibility for now. So there's two ways that this affects building services. Either as we need to extend the contract of our system, you're adding to your interface. You start building these methods with bigger and bigger parameters, or these methods with more and more camel cases that describe more and more complicated queries, right? So eventually, you may end up building this homegrown database yourself in your service. You have a database behind it, but to make your interface to all your systems, you build this crazy homegrown database that is of your own design. And adding more data to this God service that you've created, just amplifies the problem. You have different types of data, different angles, different looks, different slices and dices. You're adding more functions, more parameters, and then you've got this weird shared database. And depending, if you're tired of dealing with that kooky homegrown database, a lot of times you'll build a service and says, no, just give me all the data. I'll take all of it. I'll cut it up how I need it. I'll put it out there in my own format, right? And the problem with this, when you start moving data sets around your organization en masse, is that you get this divergence of data over time. So I've got the data, and I'm changing it, and I'm updating it, and every so often I get it from you, but you've made a change, and I didn't know about it, and now we have this divergent data. So the order service may not agree with the stock service, and fulfillment service may not agree with either. And now you're in a very complicated mess. So really, the more mutable copies of your data that you have in your enterprise and your organization, the more it will diverge over time. And you get into this cycle of inadequacy where you build your nice, neat service. You've got all your well-described functions and methods, and you realize maybe the contract's a little too limiting, so you change it and broaden it. But it's not quite a shared database yet, so you just kind of loop in here for a little bit. Eventually, you realize, oh my God, we actually are kind of re-implementing the database in this service. What do? You pay money. You re-encapsulate, you make a new service, and you keep going. Or you just get all the data. It diverges. Oh, we got to centralize again eventually. And this cycle probably puts a lot of money in a lot of people's pockets in the federal government space, right? Booz Allen probably makes a ton of money on this. So what you've got here is you've got these forces in the real world where you want to keep your data accessible. You want to kind of keep it loosely coupled. But you also have to constantly fight against this divergence, this evil thing that's lurking out there and you may not know about, right? So you've got this kind of tension between a shared database and a services interface, and there's really no perfect solution, right? So there's no way around these forces. They exist, but you may be able to make a better set of trade-offs, right? So is there a better way, right? So we go back to thinking about how data on the inside versus data on the outside. If we make the data on the outside, the data that's shared between these services, a first-class citizen, and we separate our reads and our writes with an immutable stream of data, you can start building these event-driven command query systems, adding stateful processing to it, and you can build these small, tightly bounded services that share data in a pretty extensible way. So your writes go to the owning service. The service that owns the contract will just subscribe to the data that it needs, right? Views can be materialized within the service on demand. Events come from a central shared narrative, so everybody who is reading from this shared set of data is getting the same data. And then adding a stream processing toolkit allows you to build these streaming, real-time updating views inside of your service. And that's where Kafka comes in. So Kafka being an immutable, distributed, partitioned commit log that can handle the volume of a modern organization starts to allow you to decouple these systems. So you have producers of data and you have consumers of data. You have these off-the-shelf connectors that you can connect to legacy systems, pull data in or write data out. And then you can add a streaming engine to this for real-time updates of all these systems, right? So the log is central here. So Kafka is essentially a messaging system. It moves data between producers and consumers. However, it can scale to petabytes of data. It holds the data. So it actually, unlike a traditional messaging system, when you ask for a message and receive the message and then the messaging system deletes it because you've acknowledged receipt, Kafka will hold on to it. It allows multiple consumers and consumer groups to grab it. It's got built-in fault tolerance. You can replay back over the data. So in this model, scaling becomes a concern of the centralized set of brokers. The more brokers you have, the more aggregate bandwidth you have, the more messages you can handle, and the more consumers you can service. Services naturally load balance. So part of Kafka, if you have multiple consumers that are organized into a group, they will each receive a share of the data because the data is partitioned. It's also fault tolerant, so a failure of any consumer in a group lets the other take over where it left off. You can replay the log, go back to any point in the shared narrative and play forward. This is great for testing out new models or restoring old systems or keeping things in sync. And then there's this idea of a compacted log that Kafka provides, where you can configure your stream of data to actually only keep the latest value for a key. And that should sound familiar because that's exactly what a database does, right? It's just the current state of everything. We update a key, we lose the old one. So using all of this and putting Kafka here at the backbone. Sorry, color is weird here. We've got connectors, producers, consumers, and the streaming system. This is a place to keep the data on the outside as an immutable narrative between your services. Now, if we add stream processing to this, Kafka ships with a library called Kafka Streams, which is a general embeddable streaming engine. It's just a Java library. That's what it means when we say embeddable. It doesn't require a stream processing cluster like Spark or Flink or Apex. So it's also very general purpose. The job of this stream processor is it's just a machine for combining these events into useful things, right? So you can also think of it maybe as a database engine designed to process streams of data. So like you could do a query in a database engine that says, show me the maximum price from the orders where the currency is Great Britain pounds, but then the streaming section comes in over here. You can do it over a window, and you can update it every so often. Kafka Streams features windows, views, joins, filters, aggregates. These are things that you would expect in any kind of stream processing system. But what's really neat about it is you can take your streams of data, and if you're from the database world, you might think of that as your fact table, and you can take your dimensional data from other systems. And if you know about star schemas, you have this one table that has all these events that you can then enrich by joining with other things. So Kafka Streams has a similar idea. Have your streams of events, enrich them based on some keys that are held also in Kafka as compacted streams or tables. Join them up, and you can create these derived tables from that. So essentially what's happening here is your event-driven service will be acting as a system to join these events to these enrichments, or to join events together. So if you're looking and waiting on an order where the payment is confirmed or another event, you have to wait for this other event, that's just simply a join. Just listen to the event topic, and when you get a key that matches, you know that that is an event that happened, and you join it and publish it. So you can also pull data in from legacy systems. A common use case that we help out with is mainframe offload. So you can actually use Kafka Connect, which is this framework for moving data into and out of Kafka, to connect to something that's legacy, like mainframes. The change data capture from the mainframe can be published as a Kafka log and then used in your microservices to inform things live, right? So you could join a couple of event streams and create a local data store in your service, right? So if we're doing fraud service, we would need purchase events and payment events, and we could build a model about what that looks like, and then there are thresholds that that model informs us of, and then we can, publish those events downstream to an alerting model or an alerting service. You can do projections of your events, right? So you can actually take the real events and turn them into a view and are directly queryable from within your service. So as the events that your service is listening to come in, its view's changing live up to the message. So you can build a queryable state interface on top of your service. So Kafka and Kafka Streams should be thought of as this tool for processing or materializing shared retentive data streams. But sometimes you do have to move that data, right? So sometimes it's got to go somewhere. Maybe you're doing a large ad hoc query. Maybe you're archiving it. You have a mandate to move it to Amazon S3 or something like that. So you can use Kafka Connect to write the data out. And this kind of agility is really key to this system. If you have services that are running and the data is being updated, you have the agility to move it to whatever database you'd like. So if you are being audited, the auditors use, I don't know, SQL Server. You can take all of your data and just write it out to SQL Server tables, right? That's fine. Kafka Connect can do that very, very easily. It's a single properties file, and you launch the process. If you wanted to take your fraud service and index some of it, you can send all that data out to Elasticsearch, because maybe Elasticsearch has some really good interfaces for doing these kinds of searches. So you can connect databases together. So as a source, maybe you've got data over here in Oracle, and you want to put it through your streams processing system, join it with other events that are happening, and ultimately write it out to Cassandra. That's a very common thing to do as well. So Kafka can be this extensible, reliable system to move data between systems, as well as the answer to the stream processing data dichotomy. So when you build your services, consider more than just a RESTful service, right? Maybe event streaming is appropriate for how you build this. REST is great. Sometimes simple is easier and better. The Kafka Streams queryable interface can be implemented as a RESTful query interface. That's fine. But remember that the data systems that you're dealing with are designed to expose data and enhance it and amplify it, and your services are all about hiding it. So keep that in mind as you design these. Realize that most data in modern organizations is shared and will add complexity as you start to move things around and interface with it. Embrace that the data does live and flow outside of your service, and you have to design for that. And avoid data services that have these complex amplifying God interfaces that you constantly have to expose and extend. And you can kind of avoid that by sharing your data through these immutable streams, right? So if all of the data that these services share are available to any of them in an immutable stream, and they can do derived views on that, they can do these materializations on demand as they need them, you're going to avoid that data diversion. So a stream processing platform provides the middle ground here, where your shared database may not be able to scale, but it's great about divergence because it's one set of data, where your messaging platform may not also be able to scale, or you have copies of the data everywhere as well. And then your data and your services interfaces have great loose coupling, but are constantly re-implementing that database over there. So we feel that Kafka can balance the dichotomy that these two systems are constantly fighting against each other about. So just remember, react to events, right? Leverage the asynchronicity of your events as they come through. Don't really rely on another service. Build immutable shared narratives on top of an immutable data system. Decentralize the work. Evolve intelligently, so only use the data that you need right now. So as the data comes in, you can select certain things, a couple fields here, a couple fields there. You can add them as you need. And rely on that fact that you have the data in the central log and can potentially keep it there indefinitely if required, because you have these tools called compacted logs that hold the latest state. So that's the event-driven backbone, service backbone. I can take some questions, and we can have a discussion if you'd like. Yeah.
So if you're migrating like common shared database to this thing, so you still have to go back and push all your existing data into Kafka.
Well, that's what's kind of the beauty of this, is if you wanted to sort of dip your toe into the stream processing, and you can, like I said over here, use only the data you need today, right? And focus on just what you need right now. So let's say you wanted to implement a service, take some functionality out of your monolith and just implement that as a service, right? The data that service requires can then be materialized into Kafka as taking the table out of the database and dumping it into Kafka, and then subscribing to the change data and make that change data available in Kafka. And as things are updating, the table will be updated live. So your monolith and your database that's over here is still updating and getting the data, but the data you require is also available in Kafka within a millisecond or two. So your service now is informed of the data it needs. And that's the pattern you can use to sort of step away gradually, right? So re-implement a new service over here with a new set of, maybe even the same set of data, right? Or that data plus some more. So it allows you to not have to forklift upgrade the whole thing and dump it out and start over. You can kind of take it a little bit at a time. Yeah.
What data redundancy? How do you deal with that?
Redundancy?
Yeah, I mean, like, for instance, I know it's too generic a question, but sometimes the orders include, item information about the actual, whatever you sell, services and stuff. And there's another one that is actually flowing with the services. We have a metadata that actually can.
Yeah, so we didn't really get into it because this was sort of an introduction on how this works, but Confluent provides a schema registry that comes with the platform. We're a little opinionated. It's like one of the few things we're actually opinionated about is we've picked Avro as our schema deserialization and reserialization library. You can enforce schema evolution over time. With your question of maybe some data sets have similar fields, you could use Kafka as a tool to maybe normalize both of those together, right? So if you do realize you've got duplicate data here and there, write a stream processing app to join them and discard the duplicate fields, and then you've normalized it to a publishable schema that then can be made available to anyone else as needed. Yep. We got 5 minutes. I was a little fast.
Yeah, so I would just say there's,
Yeah.
so this is very microservices centric talk.
Yep.
Right? This didn't go really deep
Nope.
into the Kafka side of things. We're seeing Kafka used all over the place in microservices architecture. So this is sort of understanding why that is. That was the attempt. If people want to dive into the Kafka aspect, you can ask a question now. We'll be around
And I would say that
to-
this is a really good primer on why Kafka exists for a couple of reasons. It helped LinkedIn detangle their services issues, but also it kind of gives you a primer on, hey, I could see how this gets used across different industries. So some of the customers I work with are banks, obviously federal organizations, biotech, travel companies. There's something like 35% of the Fortune 500s have Kafka deployed in some way or another. So it's a pretty exciting piece of technology at this point.